Saxon Algebra 1, Lesson 64. Welcome to the end of week 17. Today we're going to talk about a mathy word that you understand even though you don't know it in a mathy context. It's called domain. Using math words, here's the definition of what domain means. It's annoying. I'll just tell you that right now. The domain is a set of permissible replacement values. Ugh, what does that even mean? I'll explain. I'll give you a minute to finish copying though. Let's say that your mother asks you what you want to have for dinner tonight. Now, your family may be different and unique, but in my family, that is not a question that is as wide open as one might think. For example, if I ask someone in my family, hey, what do you want to have for dinner tonight? There is an implied list of things that we're just not going to have. For example, we're not going to have Lucky Charms cereal. We're probably not going to have cereal at all, but we're definitely not going to have Lucky Charms. We're not going to have ice cream. Not for dinner. We're not going to have fried camel tongue. We don't eat that. And we're not going to have locusts. They're just not things that we have for dinner. They're not permissible replacement values for the question that I asked. What I'm talking about is, do you want spaghetti? Would you like a stir fry? How about some pizza? Or more likely me this week, would you like soup? These are, to use the language of our gross definition, these are permissible replacement values for the question, what would you like for dinner? So this is the domain of acceptable answers when I ask, what would you like for dinner at my house? Now, maybe at your house, your domain would include some of these things, but my domain does not. So domains can change from mathematical situation to mathematical situation. You don't just pick one and stick with it for life. They can change and adjust, and we have to define them. And in this lesson today, we're going to start doing that in a very simple kind of problem. So domain means the permissible replacement values. If you just remember this dinner list thing and just think of what are things in your family that you're not going to have for dinner. You're just not. We might have waffles. That's acceptable in our domain. We have strawberry or peach shortcake sometimes for dinner in the summer. So that's in our domain. But these things are not in our domain. Okay. Flipping. I wrote so big, I used up all my page. Okay, example 64.1. Now, these problems are really simple mathematically, but what they're going to do is allow us to play with this idea about domain. What we're told to do is graph the solutions to this inequality, x is greater than 2, and we're told in a little coded way that the domain equals the real numbers. Now, the way that we draw that is we draw a number line. We know it's just a simple number line because there's no y, it's just x. So we know, okay, this is going to be simple. We go and we graph in the 2. We don't need a bunch of extra numbers. When we graph the real numbers, that means we want all the little tiny fractions around and next to the number, but we don't want the number itself because there's no equal sign there. So we circle the 2 and we draw a line like this. And what that says is, yes, give me all the fractions and decimals and tiny little numbers in between there that make up the real numbers. And you remember that chart we made with all the squares fitting inside of each other? We're including all of those numbers in here. So the natural, the wholes, the integers, the rationals, and the irrationals are in here too, right? Because they're all part of the real numbers. So that's why we draw the arrow, is to include all those little bits in there. Okay, that's the right. So when we graph the domain of the real numbers, it's an arrow, okay? Let's try another one. This time, x is not greater than or equal to 3, and our domain equals the integers. Okay, integers are different than the real numbers. The integers are the set that's like -2, -1, 0, 1, 2, and then dot, dot, dots in either direction, right? Okay, so we also have to fix this. If x is not greater than 3 and it's not equal to 3, then the only option is x has to be less than 3. So we draw this in. Let's start by putting 3 right there. Okay, x is less than 3, so it doesn't include 3, but it's integers only. So we fill in, and how far we go is up to us. But we want values for x. We want to show values that are less than 3, that do not include 3, because x is not equal to 3, but we're only choosing integers as our solution. Okay? So when we're graphing the domain of integers, we're using dots. Arrows, dots. The arrows capture all the little bitty numbers. The dots focus on just the numbers that are in our domain. Oh. Different, right? This is correct. This is correct. Let's keep going. There are quite a few of these, but they're pretty painless, don't you think? And at the end, I'm gonna give you a summing up of these rules that we're exploring. Okay, this time we're asked to graph x is greater than or equal to -1. And again, John gives us a semicolon, and then he writes domain equals the reals. When you're doing these problems in your homework, you don't need to write it all out, but I do want you to write this, domain equals the reals, okay? Versus the integers, which will be an I. Sometimes John will give us a subset of the integers. You'll see that in a future problem. But we're really just going back and forth between the reals and the integers. Those are the two options. Okay. This time, x is greater than or equal to -1. Domain equals the reals. So I'm going to draw -1 in. It's greater than or equal to. So I shade in this circle to show that it's equal to as well. I want to include -1 as part of the solution. Now I draw the arrow going this way. Okay? If you want to put in more numbers, you can, but as long as you have in this number, it's fine. This time we included -1 in our solution, so I colored it in. Notice that last time we did not include the actual number, so I put an open circle. That's an important rule. Again, I'm going to recap all these at the end of this lovely lesson, so you'll see what I mean. Example 64.4. I think there are 7 examples. Yeah. They're fast though. Okay, ready? This time x is less than -1 and the domain is positive integers. Okay, so let's take a look at this. This says we're only allowed to use positive integers as our value for x. But if we graph this for the integers, let's say this is -1. I usually put the number that shows up in the inequality, I put that around the middle. It's less than, and it's integer. So that means I'm going to be dotting like this, right? -2, -1, -3, -4. Oh, I did that wrong. 1, 2, 3, 4, 5. Sorry. I lost my ability to think. And we're saying we want values for x that are less than -1, but are only integers. But look, these are all negative integers. So this is not going to work. Our solution is either the null set or the empty set, or we write no solution. Because we see there's no way that we can have an answer that's a positive integer. So these values that we calculated are not within the set of permissible replacement values. They're the Lucky Charms and the fried camel tongue of my dinner domain. They don't work. Okay, this one is called the null set, and this one is called the empty set. This is 3 ways of saying the same thing, which is, Houston, we have a problem. All right. I think I can squeeze in one more right here. 64.5. We're going up to 7 though. We want to graph x is greater than or equal to -5, and the domain is, again, positive integers. If you're doing this in your homework, you can abbreviate that, but you need to copy the domain down onto your page so that it's right in front of your face when you go to graph. And again, make it write d equals pi if you want. You can abbreviate it, but write something down. All right, so x is greater than -5, but we're only allowed to graph positive integers. Integers means dots. We know that, no arrows. We know that we could go all the way down here to -5. I'm going to draw a bunch for this one. We know that we could start here and we could start dotting these, right? The problem is all of these guys are not positive integers, so they don't work. Here, though, we would continue making dots, right? These, I'm going to make them bigger. These are all perfectly fine because these are positive integers. Remember that 0 is neither positive nor negative. It's just 0. So this is the solution. These don't work. Looks like I'm making stars now, doesn't it? I'm crossing them out. These do work. So this would be our solution. Okay? So sometimes our domain makes it impossible to have a solution. Sometimes we still have a solution, but it doesn't include as many as it would have if the domain was different. Two more. They have a slight wrinkle. Okay, we're asked to graph x plus 2 is less than 0. Domain equals, and I'm going to use my own abbreviation guidelines, domain equals the real. So that tells me this is going to be arrows, right? But the problem here is that x is not by itself. So first we have to use a little algebra to clean this up. I want x by itself, so I'm going to subtract 2 from both sides. That's perfectly fine to do in an inequality. We get x is less than -2. Now we're ready to graph. Domain equals the real, so that tells me it's going to be arrows. I draw in the number somewhere in the middle. It does not include -2. There's no equal sign, so that's an open circle. And then it's less than, so it goes that way. Those are the lower values of x, right? Okay, that's correct. And then, last problem. X minus 3 is greater than or equal to -5. Semicolon, domain equals the integers. Fix the algebra, add 3 to both sides. X is greater than or equal to -2. So here's minus 2. X is going to be greater than, so it's going to be going this way. I'll put in 1 here just so we can see it doesn't go that way. I'll put in, oh wait, minus 3. I go crazy sometimes when I'm writing my minus numbers. This is minus 1, 0, 1. Let's give it a 2. I feel good about that. It is integers, but I can include minus 2 because that equal sign is there. So it goes like this. Integers is somewhat frustrating to graph because there's no way of showing it keeps going. We just have to set up our graph so that that's implied, right? Like I wouldn't, I just want to create the sense that it's going that way and it's not going that way. So I show enough of the critical points that I establish that. I would say show at least 2 points. I probably went extra by showing 5, but if you show at least 1, I would say that is the minimum amount you could show and still have a good graph for this problem. You're showing clearly it's not on minus 3, but it is on minus 2, and then it keeps going. All right? This is correct. So now, let's write our rules. When we are graphing the reals, if it is just the inequality, it's an open circle with the arrow. If, and I'm going to do this, so you know it's for both of them. If it includes the equal sign, then we color in the circle and go that way. All right? With the integers, if it's just greater than or less than, then we have to skip the number in question, right? That number is not included. But if we are including with the equal sign, the actual number, then we can include it. Okay? And this is always a little unsettling because students feel like, well, that's just weird. You just missed the first number. That's the way it goes. So these are some little rules for the road that sum up our graphing strategies given the different domains. Arrows, polka dots. That's how I refer to them. I just say dots. I'm not going to write that all out. That's the shorthand I use to describe them, but this is what I'm talking about. I'll talk about the arrows, and then as an open circle or a dot, a closed dot. You can color this in more if you want. And then integers, it's dots. Do we include the first number or do we include the first number or do we not? Okay, guess what? Lesson 64 is over. I hope you enjoyed it half as much as I did because I thought it was great fun. Okay, that's done. Goodbye.